Boom! What's up, everyone? Welcome to Simulation. I'm your host, Alan Sakyan. Very, very excited and blessed to be talking about imaging the cosmos with adaptive optics and so much more. We have Dr. Franck Marchis joining us on the show. Hello.
Hi, how are you?
Thank you so much. Super excited.
Thank you for having me.
Thank you for coming on. Thank you for Jill Tarter, for introducing us. We love SETI so much.
Thank you, Jill.
Thank you, Jill. Thank you, Jill. Thank you, Seth Shostak, all these awesome people we've had on the show that have been teaching us about space and the cosmos and exploration. And we're really excited to have you now. Franck's background for everyone. So it was 11 years at UC Berkeley in astronomy, 12 years with SETI in astronomy, exoplanets, outreach, all this great work, and now 2 years with Unistellar that are democratizing citizen science. We have this beautiful telescope here that we're going to be unpacking the tech and all this cool stuff as we chat. We're going to get to this later, a little bit later down the line, but we're gonna start with your career and all this cool stuff about Io and asteroids and exoplanets. And even before we get to that, I want to ask you, because we love asking our guests this question at the beginning, is this big history take on reality. Okay, we find ourselves as stewards of Earth after this long period of evolution. Mm-hmm. And what is your current synthesis on the state of humanity?
Oof, that's a very deep question. It's gonna take me 1 hour to answer to that. Now, my short is that I'm a very optimistic person. And in fact, despite all the criticism we hear about, all the challenges we have right now, I think we are in the golden age of humanity, because we're really the moment where our planet is covered with all these humans. We have all these great ideas, and we are all connected thanks to the internet. And we are exchanging ideas way faster than what we used to do. Think about it. 400 years ago, if I wanted to send you just a comment, it will take months to a letter to come to you, right? So the speed now is like instantaneous. So we can basically exchange information very quickly. So our humanity, us human beings, we are working together to solve our problem. And yes, true, we have a lot of challenges. Climate change is a big one. We have a lot of political instability in the world. But ultimately, we all work together to solve them. And I love living in this moment, in this era. Because I've seen too the before internet and I've seen the after internet. I'm telling you, I love being in the after internet because I see the acceleration of the pace of ideas and exchange in the world.
That's a beautiful synthesis. I love how you target you're talking about the paradigm of collective learning and the dissemination and communication of information and knowledge being much more accelerated now, and that being a huge way that we're being able to advance our ideas and creativity faster around the world. I like that a lot, and the globalized world also makes it easier to distribute these products and ideas and services around as well. I like how you took us there. Okay, so now let's jump into what got you excited about astronomy when you were young. How did you figure this out about yourself and then get on your path to UC Berkeley and whatnot? Yeah.
Well, that's a long story, and once again, I'm not gonna tell all of it. I do remember when I was a kid, my father bought me a small telescope. And I looked through this telescope, I saw the planets, Jupiter and Saturn. I do remember vividly as well that once he brought me to a telescope to see a lunar eclipse. And before the lunar eclipse, we also looked through the big telescope. It was in Toulouse Observatory at the time, and I saw the ring of Saturn.
Yes.
And I do remember that vividly, and I still have this image imprinted in my retina, I think, because that's been the moment where I realized, wow, there is stuff over there.
Yes.
There is planets, there is world. And that's kind of changed the vision I have as a kid. And every time I was looking at the sky, I was wondering, there is a planet maybe over there. We didn't know there was planets at the time, but I was looking at stars and thinking about planets and worlds. And then, of course, I started reading science fiction. Asimov has been one of the big science fiction I read, science fiction writer I read. I read a lot of the Dune. I read a lot of books of science fiction and talk about science fiction with my friends. And from science fiction to the stars, of course, I went to astronomy. Mm-hmm. And astronomy was not really kind of, I mean, I love astronomy, but I've been very quickly disappointed by my telescope. And so I wanted to do astronomy, but I wanted to do astronomy to change astronomy, to make astronomy better. Yeah. And a very long story, but let's shorten it. I went to see a professor at the University of Toulouse called Sylvie Vauclair. And I remember I was finishing my bachelor in mathematics at the time, and I wanted to go back to physics and astronomy. And she told me, you know, maybe you should consider working on something related to data processing, powerful new optics that we have. There is something called adaptive optics. And adaptive optics is a way for us astronomers to get an image of a target, like if you telescope, the ground-based telescope were in space. Yes. I remember she introduced this to me like that. I was wondering, how do they do that? It's not magical. There is an atmosphere above us. Yes. How do you do this? Well, they do
moving targets.
And moving targets. and basically adaptive optics is the way to do this compensation, this correction in real time.
Yes.
And that's basically excited me, because that finally I will have a telescope where I will be able to see details in the cosmos and be able to see moons around asteroids, volcanic activity on Io, and all of this. That's where it started.
Oh, that's so good that you had that influence that pushed you into adaptive optics and further engaged you in astronomy. And I love how you have that same story as so many, including myself, of seeing Saturn's rings, and that the sense of awe that comes from that is just profound, and that's its own world, like you said, and that's so interesting to me too. Every single one of these celestial objects in even just our solar system is its own world, and that's so exciting to think about, and to be able to image them accurately, precisely, so important. And then you got passionate about that and pursued it. So now, okay, I want to also mention another one of the kind of principles that you brought up here was that adaptive optics is basically one of the most important keys, if not the most potentially important key in the data processing side of imaging. And there's a lot of variables that go into it, like you started pointing out, and I'm sure we're going to unpack them more, especially as we get into Unistellar and whatnot. But okay, so how did that lead you into the UC Berkeley and then into the SETI?
Oh, well, so I did my PhD at ESO, the European Southern Observatory. I was working at the 3.6 meter telescope in La Silla. I have a very interesting PhD because I was spending 2 weeks or 3 weeks sometimes at the summit in the middle of the desert of Atacama, talking only to astronomers, and then going down to Santiago, that's where I was living, to have a social life and also to travel. So my work as a PhD candidate was mostly isolated over there and learning how to use adaptive optics, how to process images coming from adaptive optics. And this was the first adaptive optics system available to the community. So we have astronomers from all around the world coming to this place to use this adaptive optics system. Its name was Adonis. That was the name of the adaptive optics system. And I spent a lot of my time fixing it, making sure it works. It was a prototype. We had these very complex detectors that nobody have really used. They were coming from the French military for some parts that we didn't really know how they were working. So my PhD was about this, learning how to use adaptive optics and feature the capability of adaptive optics for the solar system, for the study of bodies in our solar system. So we observed Uranus and saw satellites around it. I observed Cleopatra and saw that Cleopatra was made of two...
Is that the moon of Uranus?
No, Cleopatra is an asteroid.
It's an asteroid.
Which has a very typical dog bone shape. that we
The
saw.
bone shape,
Yeah,
yes.
that we saw.
The bone is one of the more common asteroid shapes.
It's
No?
kind of a shape that we see more and more now. The bilobate shape, we call that. There is two components together.
Yeah. Interesting.
And then we saw, and then I, after my PhD, I basically got a phone call from Imke de Pater, professor at UC Berkeley.
Cool.
Telling me that at United States is creating what we call the Center for Adaptive Optics, and they wanted to hire all the people who have been working in adaptive optics around the world.
That's so great.
We all met, in fact, after in the US. Colleagues of mine were working in Hawaii or in Caltech or at UC Berkeley, and I worked at the Keck telescope at the time. My first 5 years,
ground-based telescope.
The large 10-meter class telescope on the top of Mauna Kea.
That's a 10
meter.
That's huge, yeah.
With an adaptive optic system.
With an adaptive
and that's another scale. Yeah. We went from 3.6 meter to 10 meter.
Yeah.
And that was fantastic, because then suddenly you have the capability of a 10-meter apertures in terms of resolution power. So you can see volcanoes on Io.
Yeah, this part's so crazy. But okay, before we get there, two things. First is, it's crazy that you're pointing out this very interesting aspect to your PhD work, but likely many people pursuing whatever their thesis is. In many ways, they surround themselves in sometimes in just small groups of the people that are building like the adaptive optic system for you. And then you guys, how many weeks? 6 to 8 weeks at a time?
Yeah, sometimes, yeah.
So like 6 to 8 weeks at a time, you're giving your mind the ability also to be quiet, because if you were going out all the time, if you were always around other chatter, it would be very potentially distracting. But you gave your mind the time to kind of hone in and get really good at the craft. Some people can't handle that. They need to be around other people that are not PhD astronomers. But so that's very interesting. And then the next thing that I thought was very interesting is the United States Adaptive Optics. What was it again? The group?
CFAO, the Center for Adaptive Optics.
Center for Adaptive Optics, CFAO.
Funded by NSF.
Funded by the National Science Foundation. Okay. So how cool is it that then they went and, the United States identified and the NSF identified that there were brilliant people around the world working in adaptive optics, put them together, and then you realized again that you know nothing, and then other people know so much, and that you can learn from each other and whatnot. And I'm sure that then you started teaching us about what was going on at Keck in Hawaii. Okay, so when you start putting together these, with a 10 meter mirror for absorbing light, reflecting light, you can really see the volcanoes on Io. Io is the 4th largest moon of Jupiter. It's
the closest to Jupiter.
The closest to Jupiter.
It's a very special one.
It has like 400 volcanoes.
Oh yeah.
And it shoots sulfur in like plumes. Plumes of sulfur.
And the surface is regenerated every 10 million years, basically. It's a very young surface. There is no craters on it, because the volcanic activity is so intense that the entire surface is young, and there is volcanic structures on it. So when I use the 3.6 meter telescope, we observe Io, and we saw this colorful, this powerful flash coming up. So I remember I had this map, and I used very complex data processing to see this, and I was not really sure. I was a young student at the time, and I was not very sure that I was seeing something real, or it was an artifact of my data processing. We were very lucky, because at the time we have an artificial satellite, the Galileo, in orbit around Jupiter, which was observing Io at the same time. And one day we got an image from the Galileo spacecraft. And this Galileo spacecraft, I observed Io, the same side that we observe from the ground. And I could see that all my tiny spots were seen by the Galileo spacecraft. And I have the cover of a very famous planetary journal, where basically you have the two images, adaptive optics Galileo spacecraft, and you can see the two volcano, the ring of fires of Io volcanoes on these images that look kind of similar. So that was the first step. So yeah, we can see volcanoes from the ground.
It's a huge scientific confirmation. And we're blessed to have Galileo.
And it's also, that was basically what we needed to confirm that we can also indeed find see volcanoes from the ground using adaptive optics. Then then I use the Keck telescope. So when we observe Io with the Keck telescope, it's another order of magnitude because the size is bigger and it was a better adaptive optic system. So the resolution was 3 times better in terms of image quality. It was even less blurry, okay?
Yes.
And the first observation, the first night we observed, 19th of February 2001. I know this because it's kind of a big
deal,
a big moment for my. That was the first time I was observing at Keck. So we saw Io, I saw this beautiful satellite, and we observed it 2 days later. Io orbit around Jupiter, showing the same hemisphere. Yeah. So if you in 18 hours roughly. So
18-hour orbit.
Yeah.
Oh,
so if you observe it 24 hours later,
fast moving.
Yeah, it's It's very close.
Yeah, yeah.
And it's just close to this gigantic planet.
Exactly.
And it has Europa, which is forcing Io to have this eccentric orbit. So when it's orbiting around, it's basically being squeezed all the time. That's where come from the volcanic activity.
Oh, interesting.
Because the interior of Io is squeezed all the time, and this squeeze is not perfectly elastic material. It's rock. Mm-hmm. This heat has to escape, and they escape using volcano, making volcano.
So that's the geological and astronomy science of
together.
Things. Yeah.
So we saw 2 days later the same kind of hemisphere, and it was completely different. There was this gigantic spot in the middle. We thought we were pointing on the star at the time because it was so big that we thought like, oh, we made a mistake, and we're pointing a star. And then I look at the low level, and I saw Io, and this was kind of a gigantic pimple on the top of Io, and that was a volcano.
Plume.
A plume. It's not a plume. This one we saw the heat of the volcano at the time.
That's crazy.
It took me months to find out that what we observe one of the most is in fact the most energetic eruption I've ever seen on Io.
Yeah.
He was very young. It probably had just happened in less than a few days. So we saw something super bright, like the beginning of a very bright eruption.
So cool.
In 24 hours, an area as big as Los Angeles were covered with magma on the surface of this tiny satellite. So that's
the size of LA. Yeah, that's
the size of LA. Yeah.
Whoa. Okay, so this is a very fascinating celestial object in our solar system because it's the most geologically active, we hypothesize, and we're pretty sure. And you have to, the hard thing about Keck and all these other observatories is that you have to pick where you allocate your time, because you can only, unless you have thousands of these Kecks, you only have one of these Kecks, so 2, I guess. But that you can, when you want to study an asteroid, you have to, set everything up and wait for the window and look.
You need to write a proposal, convince a group of people that it's interesting research, meet them, talk to them about it. It's kind of a lobbying sometimes, and then you get telescope time. And sometimes you get half a day, and it's cloudy. Anyway, the day later.
Disaster.
But that's part of the ground-based observation. I'm used to it.
That's right. The ground-based versus the in-orbit observation. Okay, because we can, we have to do part 2 together because there's just too much cool stuff about your work to expand, and I want to make sure to get to at least the first layer of a lot of your stuff, but then we can go second, third layer, etc. more later, because you also, you did asteroid discoveries, you did a lot of work with Io and Io imaging, and then also exoplanets. And this is what we have here. We have like an artist rendering of what the TRAPPIST exoplanet system looks like, and there's how many? There's 7 of them.
Yeah,
it's 7 exoplanets orbiting a dwarf
star.
And this is how many light years? Like 1,000 away?
Yeah.
Something like that. And we'll figure it out. But this is
Just Google it.
Just Google it, exactly. And so this is one of the Kepler and K2 and just TESS is currently up and doing work as well in exoplanet surveying. And so you have another project, Project Blue, as well, which is very exciting. Project Blue is about. Teach us about Project Blue.
Okay.
Teach us about the importance of this.
So,
yes.
before I go to Project Blue,
okay, go ahead,
when
yes.
we get to when we showed that we have adaptive optics, we could observe bodies in our solar system. We started thinking, could we observe a planet around another star using adaptive optics? And in fact, there is one person who has been thinking a lot about that. His name is Bruce McIntosh. He's a professor at Stanford University at the moment. But when I moved to the US, Bruce was probably a researcher at Livermore, and we had this kind of secret meeting where we basically exchange information. You remember you mentioned that suddenly we have all these people who didn't know, who thought they were like the top in adaptive optics, and then I meet other people who also thought they were top in adaptive optics.
Yes.
And we all realized that we all have different components in adaptive optics.
That's so cool.
So we have this meeting. It was at UC Berkeley, and in this meeting we basically brainstorm, could we observe a planet like Jupiter with an adaptive optic system? If yes, how? And people start thinking about it. We started putting together a concept of an instrument using what we call coronagraph, which in this case we hide the star and then we see the surrounding of the star and we improve what we call the contrast to reach the point where we can see an object which is 1,000,000 times fainter than the star. And that's the challenge for a Jupiter-like exoplanet. And we created GPI, the Gemini Planet Imager.
Yes.
And this instrument is now in operation, and now we can see planet like Jupiter, young Jupiter, around nearby star. So now we get to the second step.
Yes, let's stay on GPI. I forgot, we should hit GPI, then do the Project Blue, yes. Yes.
So GPI started in 2013.
Yes.
And what we've been doing with GPI is to observe all the bright stars in the southern hemisphere, because GPI is in Chile, so you can see the southern hemisphere sky, and look for planets like Jupiter using GPI. And we found a few of them. We found in 2015, 51 Eridani b, which is it's the planet that really looks like Jupiter. And when I see we see, it's very important I clearly say that the word see here, I'm using it on purpose. We saw photons coming from this planet into our detector. So if I show you a picture, you will see a dark hole, it's where the star is, and you will see the planet. And we can even see the planet moving now, because we have 3 years of observation, so we see the planet moving in orbit around its star. Seeing, it's very important for an astronomer, because when you see, you get photons from the body, and what you can do is to spread the light, where we do what we call spectroscopy, and by looking the color of the light, you know what type of gas there is on this planet, the temperature of this planet, and now we know that we have seen the first Jupiter-like exoplanet using GPI. That was a big deal in 2015. I think it's still a big deal because it's not that a long time ago.
Yes.
And we continue this survey, and we're searching more and more of those and we will find more and more of those Jupiter-like exoplanets probably in the future.
Yes. Okay. So there's a couple things that you said here. So we were talking a bit about the difference between having a ground-based telescope and then having a telescope like Kepler. So then you don't have to deal with so many adaptive optics when you're on the ground as when you are in space. It's easier in space. There's more adaptive optics to deal with, like atmosphere and moving.
There is more distortion coming from the atmosphere on the ground than there is in space. In space, we also need adaptive optics for some other reasons.
Yes. Well, you're still doing moving objects and stuff. Yes. Okay. So then, your work then, with UC Berkeley with the adaptive optics, and then starting with SETI as well, and then doing more work with the exoplanets with GPI. So this is the Gemini Planet Imager. Okay, so 2013, this is built in Chile, in the Andes Mountains in Chile, And then again, this is kind of one of those things, there's only a couple of these, there's only 3 of them on the planet that can do things like, that can image the direct image of the exoplanet, because you're doing the coronagraphy, like you said. So you're versus the transit photometry of like a Kepler telescope, where you're just looking at the dimming in the light to see the planet going in front of it. Here you're actually looking at the composition of the atmosphere with GPI and these other 2 on Earth. And like, so again, it's really hard to, you put the proposal in, it's like it's all work like you were describing earlier. Okay, so GPI was 2013 until 2017-ish,
well,
but
we're still operating GPI at the moment in the southern hemisphere, and there is plan to have a GPI-like instrument in the northern hemisphere, in Hawaii probably, to be able to do the same survey for the northern star. So that's the next step. But in fact, we already think about the future. We're already thinking about the future. We love challenges, right? If I'm an astronomer, it's because I like to do stuff which are very difficult. And the next step is to get an image of a planet like Earth.
Yes.
That's what we want to do now. Now we know that adaptive optics can do Jupiter-like exoplanet. Let's try to get to the contrast of 1 billion to see a planet like Earth in orbit around another star.
Yes. Okay, quick, teach us, because there's thousands of now data points that you're looking through with what Kepler and K2 have discovered, what Tessa's discovering. You're looking at all these data points. We know there's thousands of exoplanets now, and that a decent amount of them, actually, we hypothesize about 1 in 5 is, 1 in 5 stars has an Earth-like exoplanet. Yeah. So, so this is a lot of possibility, and so, but there's one specific star system that is close to us, Alpha Centauri, the Proxima Centauri. It's a triple star system, and it's only 4.3 light years away, versus it's the closest star system to us, versus all the other ones that we've been looking at are much further, 100,000, even more light years away. So we have the possibility of imaging that and finding the Earth-like exoplanet with what you're doing with Project Blue. So you have GPI
for the Jupiter-like exoplanet.
Yes.
And the next big project is to image a planet like Earth in orbit around Alpha Centauri. So we are interested in Alpha Centauri for multiple reasons. First, because we're extremely lucky, because Alpha Centauri A and B, we can call them Rigel, Cantorus, and Toliman, that's the official name now, are a sun-like exoplanet. They're very similar to our sun, the same color, the same mass. So if there is life on a planet in orbit around Alpha Centauri A and B, it's very likely that this life will have the same type of chemistry than us, because it's receiving the same light, same vegetation, for instance. So these are one interesting part. The second part is that it's so close that it's easy to see. It's easy to see the planet because it's much closer to us. The third part, and the first point, is that it's a very close system. I mean, 4.2, 4.3 light years is not that much. The size of the galaxy is 100,000 in light years in diameter. So we're talking about something very close. It looks far away now, like America looked far away from Europe 400 years ago. So now we are scaling our perception. Okay, now we don't think that Jupiter is that far away from us. Astronomer will just tell you, it's only 5 AU, 4 AU from us. It's not that much. Yeah. We can go there, right? So maybe one day we will be able to go to Alpha Centauri A and B. So what we are doing, astronomer, at the moment, is really the map of what we have around us. We see bright stars, okay, because they're close. And what we want to do is to have a map to give to the next generation a map telling them, here, there is a planet like Earth. That's where you have to go.
Yeah, I love it.
And that's really the job, our job, cartographer. Yeah. I don't want to be the pilot in the airplane, or I don't want to do any of these things. I want to be the cartographer doing the map for the next generation.
Oh, that's such a good way to tell the story, yeah. That's such a good way to tell the story. Is the handoff to the next generation is we're a cartographer. We've mapped this out now. This is where the Earth.
Like we had very old map. I don't know if you have been to the Vatican.
The very old map.
The Vatican Museum. There is very old map from the New World. They used to call that. They were not very accurate sometimes. That's why the French sold Louisiana to the English. They thought that it was a time. There was nothing after. Now we know that the American continent is huge. Right?
Yeah.
So those maps, we are doing them now because they're gonna motivate the next generation to go there.
Yes.
So Project Blue is about collecting lights coming from an Earth-like exoplanet in around Alpha Centauri. Project Blue is about giving indication of the existence of a planet like Earth around this Alpha Centauri A and B. It's about giving to the next generation a direction, something to dream about. Because when you see a tiny blue dot in orbit around a bright star far away from us, you will have the motivation to go there. And it's probably some kids, a very young kid, instead of having the haha moment when he saw the Saturn rings, will have this haha moment when we see this picture. And he may want to become an engineer and may want to dream about how we could go fast and how we'll be able to go there.
Interesting. So this is the next overview effect. We had the overview effect of seeing the Earth from Moon, and that's the big aha moment for us. And then now this is the next aha moment, 50, 60-ish, let's hope years later, is this aha moment of seeing a Earth-like exoplanet orbiting the closest star system to us, and then giving them the motivation to become the engineers, designers, ops peeps to get us there.
And probably the next generation will have an app or some virtual reality set, and they will look at augmented reality set. They will look at the sky, and this map will be implemented, and they will be able to this system will tell you, oh, there is a planet there.
I just thought about having Unistellar in my perception. That would be so cool to have telescopic abilities within my vision, and the adaptive optics. Oh my gosh, that would be so cool. Wow. Okay, let's get to Unistellar.
But the motivation of Unistellar is not too far away from what you just said.
Yes, please.
Our goal is really to bring back the sky to the people. I mean, if you look the sky right now from the city, where 80% of the people are living now, you don't see
80% of humans, of the almost 8 billion of us, live in the metropolis.
Metropolises, yeah. So the sky is not really nice now because we use all this artificial light to light up the street and our houses, and at the end the stars are slightly disappearing.
You see like 4 or 6 or something.
San Francisco, you see 10. The best case if you're not in downtown.
And we're right next to the ocean, which is pitch dark. And we can still only see.
So we basically. This is a big problem for humanity, I think, because if you don't have the sky, you don't have the view of the sky. You don't dream. You don't dream about what is there. And people like me who become astronomers because one day they ask this question by looking at the sky from the countryside.
Yes.
They will not have this moment. So Unistellar is all about bringing back the sky to the people. So for this, we created this what we call digital telescope.
Love it.
And I can explain the technology if you want, or maybe we can just...
Let's get there after we play this. And actually, just before we play, I just want to say, bringing the sky back to the people, bringing the cosmos back, imaging the cosmos with these adaptive optics. And there's just such a big contrast between seeing 10 stars in San Francisco and being in the middle of nowhere, and when there's the moon, when you can't see the moon too, because then that brings a lot of light. From the sun reflecting off of it, but when you can see just literally a billion stars because you're in the middle of nowhere, there's nothing quite like that for ego dwarfing. I think there's nothing quite like that. Maybe some very deep psychedelic experiences, deep meditation experiences, but So bringing the sky back to the people. We'll get to some of the tech stuff here in a moment. Because to be able to, just to be able to see in these 80% of humans that live in metropolises, if they can leverage adaptive optic technology to see the cosmic perspective of these stars in the light polluted areas is so crucial. Okay, so we have, let's go ahead and let's play the video that we have,
Unistellar's telescope is a smart, connected consumer device that amplifies light to reveal the hidden wonders of the universe. Leveraging its worldwide network of users, it allows anyone to contribute to science as they observe exoplanet transits, supernovae, and much more, making astronomy the science that will unite us all.
Yes, so this is that you just had that, that side by side there and that was even pretty gracious on the left side, because more normally we don't even get that, let alone because that would give us because that I'm curious about the size, like what is the size of the mirror, the adaptive optic technology, all this kind of stuff. But you got inspired to make this in the first place. You have to have a team. You have to work with
So there is no adaptive optics in this telescope. We have been using the technology that professional astronomer has been using for years, and we put it into this device. It's integrated. It's easy to use. Everybody will be able to observe the star with it. One of the co-founders, Arnaud, is the one who got basically the idea of the enhanced vision. The enhanced vision, it's a concept of stacking together images in real time that has been collected with this device into this the camera here, and then it's projected into the electronic eyepiece here.
Yes. Okay.
So the idea here is that you mimic the image you see with the eyes.
Yes.
But by stacking them, you enhance the sensitivity.
Yes. Okay.
So you basically see with your eyes like if you had a 1 meter class telescope in your garden. In terms of sensitivity, we reach this type of sensitivity.
So the optics that you have in here are stacking the images
in
real time of the same patch of sky that you're looking at, and that makes it enhanced.
Yeah, we can show maybe a video of what we see with the telescope.
Let's do that.
I'm not gonna say where we are. So that's basically the Orion Nebula at the moment. It's a video taken with a phone into the eyepiece. So that's really what you see with the telescope.
That's the Orion Nebula that you're taking with your iPhone through the piece.
And this is where we are. We are in Las Vegas. So here, really you illustrate the power of this telescope. Even if we have light pollution around us, by using this technology and by using a complex processing that remove the background and so on, we can stack images and get to the sensitivity sufficient to see nebulas from Las Vegas.
Seeing nebulas from Las Vegas, yeah.
So this is an iconic nebulas in the northern hemisphere, of course, in the constellation of Orion. So this has been shown around. We have been showing this telescope around demos in Las Vegas, in San Francisco, in Los Angeles, etc., and in Marseille as well. So the company who's been designing this, it's based in Marseille, but we have offices here in San Francisco.
Okay, so Marseille and San Francisco is Unistellar's two headquarters offices.
Yeah.
And you have how many team members now are working on this?
Now we have 13 people working.
13 people.
Yeah.
And then you guys sold 2,000 of these EV scopes on your crowdfunding campaign. And then that's about $3 million of funding to be able to keep working on the engineering and get them out by the end of 2019.
2019.
Yeah.
Our backers will receive them earlier. We will start shipping Q2 2019.
Great.
This telescope will be available on the market in 2019.
Exactly.
Toward the end 2019. Yeah.
And the cost approximately, do you know yet?
Right now is on our website for $2,000.
$2,000.
Yeah, $2,000.
Yeah, and that is quite it's becoming quite like democratized in terms of ability to, because that cost is just going to keep dropping as well. For the technology is going to keep getting better, the cost is going to keep getting better eventually in our own optics, like we were saying earlier. This is crazy though, in the middle of light polluted Las Vegas. So on the tech side, you said you're doing the image stacking, real-time image stacking, plus you're also you're pushing the light pollution off as well. So it's kind of like two things.
It's two things, yes. We process individual image, such as we remove the light pollution and the effect of the rotation of Earth, because Earth is rotating, so the sky's orbit is rotating as well, and then we stack images. That's basically the image you see is the image made of the true photon collected by the telescope at the time of the observation. In fact, you can see, if you look at the video, maybe we can see the video, you will see there is a satellite that flew nearby Orion.
Oh, on Orion, that one. Yep.
You see here? Oh, sorry.
Was it a little back?
Slightly back, and you will see a dash line. You see that?
Oh, there's the dash line. Yeah, around stop it.
That's an artificial satellite that was passing between us and.
Whoa! So it's in the. So if you're watching, it's at the top left side of the Orion Nebula. And for those that are just listening, we're able to actually see that's one of our satellites.
Yeah.
Yeah.
So that's to illustrate that it's live. That's really, you really see what's happening at the moment in the sky. We're not cheating here. We're collecting true photons coming from the.
That's crazy.
From the.
That is so crazy. Yeah. Normally you can't see, let alone a nebula, but a satellite from. Yeah. That's crazy.
So and we also make it such as everybody can use it. I mean,
what's the size mirror in here?
4.5 inches.
4.5 inches.
Yeah.
Okay.
And it's a smart.
And it reflects. It takes the light onto the mirror.
Reflects the light. Then it goes to the camera here. There is a computer on board here that calculates in real time. The battery is here.
Battery is here.
And there is a projection device here.
And the projection device.
And you can also see the image on your phone.
Okay, so it reflects the light into the camera, and then the camera sends the image here, and the after processing. Yeah. And the processing, the computer is kind of.
It's here, basically.
In here. Okay, interesting. And then this is all coordinated through, remote and phone.
Yes. So you control with your phone. If you can show, there is a video that shows the phone and how the. So you are going to get an application you can run it now if you want. That's going to show targets that are visible at the time of where you're located.
Yes.
You select the target, and the telescope will basically automatically point toward the target. He has his own library of stars, so he will be able to tell you, yes, I'm in the right position, and start integrated and taking data. This is a real observation with the Unistellar telescope of the Dumble Nebula, for instance.
That is so high quality, yeah.
So you can
do that again because we made a mistake. Can you just explain it one more time?
Yeah, of course.
Awesome.
So the phone gives you a list of targets. You select the target. The telescope points toward the sky. Find with his own library of sky where it's located. Find the target. Start the integration, and you can see the nebula here, the Dumble Nebula, into the eyepiece or on your phone as well. And you can share the image as well. And,
that's great to be able to share.
And tell people, hey, I'm observing right now, and this is what I saw.
And this is very cool because you can actually see what, Ronnie? We good? We good to go?
Yeah.
Okay, it's all good. This is c'est la vie. That's our phrase. So great. So this is very cool because you can see which stars that you can, or stars / nebula / all this cool stuff that you can go explore, celestial bodies and objects. And then autonomously, once you select, you will move. Unistellar moves into that and then starts doing the adaptive optic processing, and then you're getting the image in the eyepiece on the phone. You can share it, inspire other people to get looking.
Get it and share your data, or you can work together. Maybe we can show the next the picture of Earth that we have, because SETI has been extremely interesting in partnering with Unistellar. Okay. Because we realize that with this tiny telescope, we get a sensitivity like if you had a 1 meter class telescope. So people can use it to observe targets in the sky when they do camping and so on, enjoy with their friends, but they can also do real science. And the real science I have is the next picture.
This is cool. I just want to say this.
Okay,
Yeah.
We can go back to this
back.
slide.
Yeah, go back. Okay,
let's go back to the, sorry.
Thanks, Ron.
So that's basically an observation, various target that we observe with the EV scope of different bodies. So you recognize them 42, the Orion Nebula. Here, this is the Ring Nebula. This is the Dumbbell. So those are real observations. This is a comet that was passing nearby Earth last year in May.
So this is like doing this citizen science to make a massive library, a catalog.
Of those bodies.
Yeah, of the bodies, yeah. So this is the cartography that's happening.
Yeah,
and
so
in real time too is very important because this changes, like if there are supernovas happening, we've missed them. These are moments that we've missed in the cosmic history. And so to be able to map everything is so important, yeah.
So let's go to the next slide, which illustrates the science that we want to do. So what the point here is that now we are going to have a network of those EV scopes everywhere on this planet.
Yes.
And we hope to have people motivated to participate to scientific campaign. So when you're gonna get your EV scope, you're gonna become a citizen astronomer, and you could, if you choose, you will get notification about events happening in the sky, like a new comet has been discovered yesterday. Do you want to observe it? You take your telescope, you be outside, you will be able to see a telescope. Or even if you have a network,
that's
you're
so
observing and you get a notification about a new comet which has just happened or just been discovered, or a new supernova.
Oh, this is so cool.
Or you will be even the first person to observe the afterglow of a gamma ray burst. This will be possible with this telescope.
I love it. These are the only notifications I will enable on my device. Yeah, because I don't use notifications.
And a lot is happening in the sky.
Yeah.
It's interesting because now we have all these surveys that observe continuously the sky, and I have a hard time keeping track, for instance. All the stuff happening. Like new bright stars popping up, new asteroid, new comets, the flyby of an asteroid. An asteroid recently has this kind of weird activity and become a comet, and we don't really know why, because now it has two tails on the top of that, so that's even more complex. So this is happening at the moment. And with this, you will be able to see it while you're recording data for the SETI Institute Astronomer. So as an astronomer, if I'm interested in getting more data of a new transit of Jupiter-like exoplanet, I will be able to ask the network to collect observation. And people will take data for us, send us the data, and in return, we will send them basically process data, or a kind of an explanation of what's happening, or another very crazy idea we have is to ask like 400 people to observe the same comet the same time.
Yes,
like today we're gonna do a night we're gonna observe this comet.
Yes.
And we send this notification to 400 people on this planet, and 400 of them will observe it, and then we put them together.
Imaged from all different angles of Earth as well. Put all those images
together. We are going to get the best picture of a comet taken with all these telescopes
even
together.
with some three-dimensional ability to tweak and look. It's funny that what I was thinking when I wanted to say was owning Unistellar, being inside of a place like this recording studio, you couldn't do it with it, but most of the homes, again, metropolises, so I don't know if this is quite, you could leave it on your balconies or whatever, but the idea is that you could keep Unistellar powered all the time outdoors, and then you can just enable, while I sleep for the 8 hours, for the team of Unistellar to be using this for imaging in hundreds of thousands of them across the planet, using them for imaging. And then we're talking about really building the catalog of that's so exciting.
We are thinking about
I'm gonna give you a huge hug after this. You guys are awesome. I love it.
Imagine school as well. They will have
love it.
an unistellar telescope, and you want to observe something like a comet, and tonight it's cloudy. Well, you can get access to other unistellar telescope. You will be able to do your observation. A unistellar telescope somewhere in Morocco will have a clear weather, and you will have access to it. So yes, we are thinking about that as well.
Oh my gosh, it's so cool. Oh, I love the endless possibilities with this. It's so great.
There is so many possibilities that we don't know which one we're gonna address first.
I think I guess first and foremost, the most important thing is to get the message out, get more people to support you guys, and then have you guys work on making the optics better, decreasing the cost, making the autonomous systems better, convincing people to leave them outside overnight, if it's going to be clear and not making it so it can sustain water damage in case it by chance rains, all this kind of stuff, I guess, just to get more people to want to. There's so many people that have income ability to be able to help support you guys. So that's very, very important. The amount of citizen science and what's possible with this, and just this in very many ways reminds me of how artifacts and archaeology of the human species has been lost. So much has been lost because it's just done. It's gone. It's, erosion, etc., has destroyed it, and even of other animals like paleontology and stuff, of other fossils of other animals, just gone because we haven't been able to recover it on time. So even now, there's a ticking clock of artifacts disappearing from Earth that we need to go dig up and get to understand, right? Big history. Same thing with Unistellar. There's a ticking clock of all this. You had there's galaxies and asteroids and nebulas and all this kind of stuff, that supernovas that are happening in the cosmos that we can't log fast enough into our catalog of cosmos, of the big history perspective. And that's like, it reminds me, it's like cosmic archaeology in a sense. And
so I have something that an idea. I work at SETI Institute, so I have to have something crazy to tell you, right?
Yes.
Think about it. If a species, an extraterrestrial civilization, a technological civilization, slightly more advanced than us, build this gigantic laser beam to send their spacecraft or to communicate with their station, and then one day they notice that there is life on this tiny blue dot around this G-type star called the Sun. They will not call it the Sun, probably. They will call it differently. And they decide to launch their laser pointer. Their lasers toward us like a pointer, like a beacon, saying, we are here, we are here. They're not going to do that for a long period of time because this uses a lot of energy. They may do that for a few hours. Well, maybe a unistellar telescope will catch this in the sky. And that's what we want to do as well. We want to be able to see the sky 24/7.
Yes.
Because we don't want to miss this extraterrestrial signal.
Yeah.
This will be a game changer.
Those are huge. Course. I love how many big things that you're working on. 24/7 cataloging of the cosmos, doing the Earth-like exoplanet orbiting the Alpha Centauri star systems, that you're doing the GPI and constantly doing ground-based telescopic work of imaging exoplanets and the atmospheres of those exoplanets to find hopefully life. We still have yet to unpack, what's hopefully going to happen with Europa and Enceladus, other potential spots for life. The colonization of the moon and Mars, and how exciting that is, and how we do that, geopolitically. What are the protocols we take from our civilization to the next rock? There's so many topics to still talk to you about, and I'm very excited to have.
Well, I'm not too far away. I can come back.
We would love to do part 2 with you, Franck. It's such an honor. I have a couple quick questions on the way out. Okay. First of all, a very scientific answer is, of course, no, we haven't identified, but what is your greatest imagination about life in the cosmos?
My greatest imagination about life in the cosmos? I think life is everywhere. And that's what I think, in fact, we will soon find out that life, like bacterial life, microbes, are everywhere. It's kind of a natural evolution of any environment. And we will find out that there is life on Mars, in the cave of Mars or in the geyser of Enceladus. And we find that life spread around quickly because rocks, meteorites has bring life around, and probably life is very similar somehow because of this. Intelligent life is another big problem that I have. I can talk, this is an entire hour discussion, but one of the problems I have with intelligence is that quickly intelligence will try to replace itself by something mechanical, something which is not biological.
Yes.
So I do believe that biological intelligence is a glimpse into the evolution of a species, because quickly this biological intelligence will become an artificial intelligence.
Correct.
We are creating our own. We will create quickly something that will replace us, something that we don't need to eat, something that we don't need to drink, and can travel through the cosmos as tiny cube, harvesting the energy of stars, for instance.
Ron?
I can't talk about it because what I don't understand is how come nobody sees what I see, that we are this intelligence and we are turning ourselves into this different human being, and this is virtual reality. And like what you said, just hit the nail on the head as far as what I understand, that the past, the present, the future is all happening at once, and all we're trying to find is just kind of ourselves. And does that make any sense?
Yes.
Okay.
Yes.
Yeah.
There's crucial between what both of you said. It's just that on this timeline of what we're experiencing, this biological blip that occurs is very interesting to me as well, because we're talking on the scale of just a couple million years as an intelligent life. Because after that blip becomes the artificial intelligent life, and when a general intelligence is able to go and begin exploring the cosmos, I mean, we're talking, self-replicating abilities to the extent of very strong exploration of the cosmos. So, and colonization of the cosmos, of the galaxies, and then can they even get between galaxies? And there's so many other questions to ask. The simulated realities, and are we in one? We have to move.
We're doomed. We're doomed. This is the end of life as we know it. The end of the world as we know it. We're coming into very interesting times, and I just hope the animals get to stay and continue to be animals.
Yeah, the animal.
Yeah, the
planet.
peacocks, the dolphins, the giraffes, the rhinos, the elephants, and just life in itself, which is seen. I'm not quite believing that the human is evolved.
The human ethics have to do a good chunk of evolution left prior to being able to program an artificial intelligence ethics.
But there is another path that probably we will start thinking very soon, and in fact some people are already started thinking about it. What about making our biology better?
Correct.
Changing ourselves, the biological species, so we can be, for instance, in space.
Yes.
Changing ourselves using the CRISPR technology.
Correct.
To make ourselves faster, better, and be able to travel through the star, and not having to feel the effect of the absence of gravity.
Yes.
Using what the nature has been done around. Becoming the perfect species that live on this planet without having to change it. like becoming the smart dolphin or the smart whales.
Yeah, this is the bio and neurohacking. This is the bio neuro augmentations. This is living as long as you want, because you constantly stay in the age of being 25 forever. There's a lot still left to unpack, but this is a good short bit on what your thoughts were about that. I have to ask you two more quick. This is simulation, so we have to ask you: are we in a simulation?
We cannot answer to this question.
Scientist, of course.
Of course.
but what are your
There is
wildest
no way I can
imagination?
prove it. So
about-
there is no way I can disprove
Not
it or
yet.
prove it.
Not yet.
Yeah, not yet. So I will tell you, I cannot. It's not a question I should ask my time thinking about, because there is no way I can prove it or disprove it.
What about your wildest imagination?
I don't think we are in a simulation.
You think it's base?
I will just. My wildest answer is that if we are in a simulation, let's enjoy it and make this simulation even better.
Even better. Yes, that's right. Amen.
I do.
I love it. Okay, last question is: what do you think is the most beautiful thing in the world?
Whoa, I think it's Earth. Because it's an amazing nest of intelligence and biological species living together on a very thin layers, the atmosphere.
Yes.
And from far away, it's a beautiful planet to see. I've seen pictures, I never see it from far away myself, and I wish to be able to do that.
Yes.
So I think that's the most beautiful thing in the world, yeah.
Yeah. It could even be the most divine thing that we can experience, is that we evolved here, and that it's now up to us to do what is needed in the next step of the evolution of the code of what's happening. Franck, what a pleasure this has been.
Thank you.
Thank you for all your work in inspiring people and working on such incredible feats of technology that we're very excited to help get all around the world, and help us hopefully have more awe and wonder and pass that along to children, the next generation. Here's the card. Here's the map.
Thank you very much.
Thank you. Thank you. This has been such a pleasure. Please, everyone, thank you so much for tuning in. Check out the links below to Franck's work. Check out the links to Unistellar. Go and if go and get involved more in the conversations about astronomy and about the planetary and cosmic perspective, about really awakening ourselves and our children and our next generation. Get involved in. You guys are still selling, so,
yes, we're still selling.
Please get in, if you can get involved with backing Unistellar. Get one of these in your homes and share it with your communities. Give us your thoughts in the comments below on the episode. We'd love to hear from you. Keep building out the community, everyone. Thanks, Ron, for producing and directing. This has been a lot of fun. We really appreciate you so much. And everyone, build the future. Keep supporting the artists and the entrepreneurs that you believe in. Support Unistellar, support people like us. Our links are below as well. Support artists and entrepreneurs, your community. Build the future. We love you very much, everyone, and we will see you soon. Peace.